in processors acting in your computers, and actually we will see how the field effect transistors makes logic operation in processor chips, and it is also one of the most important in analog devices when we want to make radio frequency signal transmission, for example, between Wi-Fi spot and a receiver. You will definitely need field effect transistors to generate high frequency signals and to detect it. So the knowledge of field effect transistor is the most important, I think, knowledge in all nanoelectronics. If you will have questions during the course, of course, ask it either orally or via Zoom chat. Actually, I will try to cover two observations in my talk today. The two observations are the following. First, the observation number one is called Moore's law, which was valid throughout all the 20th century, where the where the electronics in general started to develop. On this screen, you can see on the vertical axis in the logarithmic scale, you see the number of calculations per second per unit cost of computing device, which actually cover, and on the horizontal scale you see the time. This is the time scale during the 20th century, and the number of calculations per second per unit cost was increasing exponentially or linearly in the logarithmic scale throughout all the devices for computation that we had, starting for the analog machines, continuing to the devices based on electronic lamps, and continued with the devices based on bipolar transistors and integrated circuits. And one of the aims of this lecture will be to understand how this behavior, the number of calculations per unit time per cost, is associated with the other well-known trend in electronics, which is the trend to miniaturization. On the vertical scale, again in the logarithmic, which is the logarithmic, you see the size of the minimal element in the integrated circuit, the minimal size of the device versus time. And this minimal size of the device, the so-called technology node, was also increasing approximately linearly in the log scale, which means this was an exponential decrease in the feature size. And this plot can be continued actually toward the year 2020, which cover the most contemporary processors. The goal of this lecture, among with understanding the physics of field effect devices, is to relate the size of the device to its performance, to its number of calculations per unit time. Of course, during this lecture we will also cover some basic physics and learn how to model the field effect devices, how to find its current voltage characteristics. On this slide you will see the principal scheme of the field effect transistor. Sorry for the Russian captions, but I will rephrase it in English. So the field effect transistor is a two-terminal device which has resistance between two terminals that can be controlled by the third terminal. The two terminals are called source and drain. The source and drain are actually the two electrodes between which we want to manipulate the resistance. And the third electrode is called gate. The source drain space is the semiconductor. The gate is separated from the semiconductor by a thin layer of insulator. Typically, this insulator is made of some oxide. Like if the semiconductor is silicon, then insulator is SiO2, silicon dioxide. The gate is made of metal, of course, and there are contacts to the source and drain, which are also metallized. So what is the role of what is the principle of the field effect transistor? By applying some voltage to the gate, you manipulate the resistance between source and drain. Actually, the gate is electrically separated from silicon body, and it is separated via an oxide layer. So gate consumes no current. Still, it can manipulate the conduction between source and drain. And this is very important. This is the difference of the field effect transistor called between the field effect transistor and the so-called bipolar transistor. The field effect transistors are very good because they consume no current to the gate upon their switching. The analogy is like source and drain are two ends of the water pipe, and the gate is the valve that can be either closed or opened. So you can vary the position of the valve and change the permeability between source and drain. You can change the flux of water that is flowing between S and D contacts. Of course, there is no water in semiconductor, there are electrons or holes, but still the principle is roughly the same. So as you are already master students, and I think we can cover this in more detail. This is the first level of understanding for the field effect transistor, just analogy with water and valves. The second level of understanding requires painting how it is indeed formed in semiconductor electronics. You start from blank silicon wafer. So here everything below it is made of silicon. You form two contacts by doping the silicon with the opposite type than the substrate had. So for example, if the substrate was p-doped, it was hole doped, then the contacts of source and drain are doped with opposite polarity, they are doped with electrons. Then you make metal contacts to source and drain. Now you see this kind of doping, and you would like to, well, measure the resistivity between source and drain. For example, by applying some voltage between them and introducing an ampere meter between them. So how do you think would this resistivity be low or high? Does this state correspond to the well-conducting state of the field effect transistor, or it is poorly conducting? Do you have any ideas? Don't be shy to tell it in chart or orally.
Could you please repeat the beginning of the question?
The beginning of the question is, you have a semiconductor that is doped like N, then P, then again N, the triple structure NPN. You apply a voltage source to its terminals and try to measure the resistance. If this resistance large or it is small, like is it several mega ohms or it is several ohms?
It is large.
Could you explain why should it be large? What's your opinion?
Because we don't have any gate voltage here.
Oh, how it is related to the presence of gate voltage? Why it is hard for an electron to travel between N and P and again into the N?
Because our channel is not filled with charges.
Okay, this is a good idea. This is a good idea. Actually, there are many explanations of why this state corresponds to the off state. Like, for example, you have an electron initially in the n-doped channel, and it wants to travel like electron to the end, but there is a very little number of electrons, little electron density, so it cannot continue traveling like an electron. So you try to inject many, but they remain very little. So this is one approach to explain the off state of a field effect transistor without any voltage. The other approach is that you can try to factor it into individual blocks. What is this block? NP. But this is a PN diode. This is a simple semiconductor diode which has a rectifying characteristic. It passes the current in one direction and doesn't pass the current into the opposite direction. What is this? This is also a PN diode, but it is reversed. It doesn't pass current in the opposite direction. So at least one of the diodes will block the current. And due to this double diode structure, NP plus PN, the whole structure will be not conducting. So now if we would like to plot the equivalent circuit for the structure, it would be like this. So we introduce a voltage source, but two oppositely connected diodes will give us no current. They will block the current. And this is the reason why this is in off state. Now why we need the gate? We need the gate to open the transistor. Assume that we apply some finite gate voltage, and this gate voltage is positive. When we apply positive gate voltage, there is plenty of electrons that want to get attracted to the gate. These electrons can come deep from the substrate. For example, they can come from the depth of the p-doped substrate. There is very little number of electrons, but there are still some of them. There are many electrons in the contacts which are n-doped, and there are many electrons in the metals. So all they want to get attracted to positive pole of the gate, but they want to get attracted there, but they cannot because they are stuck into the insulating layer. They get close to the insulating layer, then they are stuck, and they form the so-called N channel. So like your gate has plus polarity, there are positive charges accumulated on the gate, and there are negative electronic charges accumulated in the channel. And wow, it indeed works. You have n-doped contacts, and the N channel that is formed atop the p-doped semiconductor substrate. So like you have applied the gate voltage and you have changed the type of conductivity of your silicon wafer to an opposite type. And now if you plot the equivalent circuit of this device, the PN junctions would be erased. They are no more important. Your electron injected from N contact would easily pass into N channel and then get into the drain. And this state would correspond to high conductivity, low resistivity, and high current. So this is the operating principle of the field effect transistor. Do you need any other level of explanations? Do you have any questions probably? Don't be shy. Okay. If not, then I will pass to, I will sketch another possibility to explain why these on and off states are formed by painting the band diagrams, the so-called potential energy diagrams. In this structure, if you would like to plot the electronic potential energy versus the coordinate, then it would look something like that. You remember that in a PN junction you have a staircase structure for the potential energy. The Fermi level is constant. Your potential has an upward bending from the N region to the P region. Now then in the P region it is flat, and then it goes down again. So now you see that you want to apply, if you try to measure the electronic conductivity of the system, then your electron has to climb over the barrier, which is quite complicated for him to do so. The barrier is relatively high. But when you apply positive gate voltage, your positive potential penetrates here into the channel. Positive potential for electron means negative potential energy. So this barrier is lowered down when you apply the gate voltage. And your potential energy diagram looks either like that, barrier but not very high barrier, or it can even look like you have a well within the channel if you apply a very, very large gate voltage. So anyway, you apply positive gate voltage, your positive potential penetrates into the channel, and the potential barrier height is lowered upon application of voltage, which means that you make your passage of current easier. And so you see that there are many interpretations. Of course, you can make a field effect transistor that is fully inverted, and you can take it not as a NPN structure, but it can be a PNP structure, and the polarities can be indeed opposite. And this type of the field effect transistor will be open upon application of negative gate voltage to the gate, because you would attract holes into the channel. So initially you had PNP structure, then you apply negative voltage, you have P contacts and P induced channel. Your conductivity again becomes very high, but here it becomes high at negative voltage. So actually, if you take these two devices and connect it in series, then you will get the simplest logical device that make the operation of your integrated circuits. You can get a logic inverter which makes negative signal into positive signal and positive signal into negative signal. I will explain it in the plus-minus notation with positive potentials and negative potentials with respect to some middle line of the system, but in real situations you have always some grounded electrode. So now for a while, how it operates. The logical inverter is the device that should convert positive potential at the input into the negative potential at the output. It is a serial connection of two field effect transistors, one PNP, the other NPN. Let us assume that the potential is negative, is shifted to the negative values at the lower electrode and to the positive values at the upper electrode. Then this is just positive potential, like constant potential contact in integrated circuits. And now we want to make a logical operation, convert positive voltage plus V into negative voltage minus V. Why would it work? Because when you apply positive voltage plus V, then you attract negative charge carriers into all the transistors. For NPN transistor, this induces electronic channel. This induces good conduction. So this would conduct. The upper transistor feels again positive potential. More and more electrons get attracted here, but it doesn't lead to enhanced conduction because it's PNP still. So it is like a blocking stuff. If you now would like to see the equivalent circuit of the well-conducting device and blocking device, in the simplest situation you can plot it like a straight piece of the wire without any resistance at the bottom and cut in the wiring on the top. So what happens indeed, you have negative potential at the lower pin, and it is equipotential with the output because the resistance of the lower device is very, very small. And the resistance of the top device is very high. So your output is pinned to the negative bias, and you have plus on the input and minus on the output. Of course, everything is just opposite. When you apply minus at the input, the upper transistor is equivalent to the straight part of the wire, and the lower transistor is fully blocked, and your output is pinned to the positive potential, to the top wiring. This makes the logical inverter. A good home task for you is how to realize a logic inverter with just two potentials, like ground potential here in the bottom and one drive voltage at the top. This is actually how all integrated circuits work. They use only one drive voltage and one ground electrode. So there are no other voltages than drive and zero in modern integrated circuits, and the drive is roughly 0.5 volt. There are no intermediate voltages in contemporary integrated circuits, for simplicity. Just two positions, 0 and plus, on and off, nothing else. Okay, now this is the most important digital application of field effect transistors. The most important analog application of the field effect transistor is to generate high frequency signals and to amplify the signals. Now let us try to realize how it works. The current voltage characteristic of the field effect transistor in the simplest form. We will cover more complicated form, but in the simplest form it is given by current equals conductivity depending on gate voltage multiplied by bias voltage, VDD. So the current depends on the drive voltage along the transistor between source and drain in this direction, and multiply by the conductivity that is controlled by the gate. Actually, this form of the dependence enables the operation of amplifying devices. Let us try to imagine what happens with a very small signal delta Vg when you apply it to the gate. How this signal is amplified when the transistor is connected to some external load. This external load here is denoted as LC loop with tuned to the resonance, but this is principle for high frequency generators, but not so principle for understanding the amplification. So when you apply small voltage delta V gate to the gate of the transistor, then its current gets an amendment which equals the derivative of conductivity with respect to gate voltage multiplied by drive voltage multiplied by small gate voltage delta Vg. Actually, this derivative of conductivity with respect to gate voltage can be very large. So you can, if you tune the transistor between on and off state, you slightly push it to the gate voltage and your conductivity increases dramatically. So this conductivity is very large. Then this current is going into your load, and actually if the load as a whole has an impedance Z load, then the output voltage on the load delta VL would be equivalent to the input current multiplied by the impedance of the load, and it equals the derivative of field effect transistor conductivity with respect to gate voltage multiplied by load impedance multiplied by drive voltage and multiplied by the small gate voltage. So you see that the voltage at the gate was transformed at the voltage at the load, and there is some dimensionless gain factor, the dimensionless quantity, which we can call G, the gain of the field effect transistor, and for good transistors it can be much greater than unity. So the field effect transistor can make an up conversion of the voltage signals, and this is especially good working if the transistor is strongly biased, when its drive voltage is high, when it is highly sensitive, when its conductivity is highly sensitive to the gate signals, and when the load has very high impedance. Actually, for resonant loops made of inductors and capacitors, this input impedance can be very, very high at the resonance. So this is how to make an amplifier from the transistor. Making amplifiers is important to detect small signals, for example, small signal from a Wi-Fi spot that is located hundreds of meters from you, or to detect small mobile signals and so on. So high gain is important, but you can also use this high gain to make a generator of electrical signals. To make a generator, you need to make a feedback from this circuit. So you have amplified something, then you need to take a part of it and push it again to the input of your circuit. This feedback is typically made if you have two inductively coupled loops, and you can make a voltage transformer which takes a part of your transform device and pushes it back to the gate of the field effect transistor. So if you use the feedback loop, you can make a generator. And these generators typically work fine till the frequencies of several gigahertz, or for the best transistors, for the several tens of gigahertz. Of course, there could be a question how you take this initial small signal to get amplified and looped back, but these small signals also exist due to electrical noises. So you take a small signal from your noise, then you resonantly filter it and take a part of it and reflect it back to the gate. This is how high frequency electronics generally works, based on field effect transistors. Actually, I told you that you should take a good field effect transistor to make your amplifier and generator work well till high frequencies. Good means that the gain of the transistor is typically a decaying function of frequency. The transistor cannot respond quickly to abruptly varying electrical signals, and it is possible to bring an explanation to this fact. Actually, the channel of your field effect transistor is a distributed resistive capacitive circuit. So your channel is a distributed resistance and your gate is a distributed capacitance. You probably know that the propagation of electrical signals along this circuit is described by something like diffusion equation, and the characteristic time of signal propagation between one end of this circuit and the second end of this circuit is simply given by resistance times capacitance, where the resistance of the transistor channel and capacitance is the capacitance of the gate to channel dielectric, and the smaller is the resistance of your field effect device, the faster the signals propagate. So for analog electronics, you need to make transistors with small resistance channels, but we will explain this quantity in more detail in further slides. Actually, we will find the switching time of the field effect device for more rigorous considerations. Do you have any questions now? because otherwise we will pass in more detail to the theoretical description of the field effect transistor current voltage characteristic. Anything, probably stupid questions. Okay. So I think with the background that you have from the previous lectures, you have enough to build a current voltage characteristic of a field effect transistor. This will be very, very simple. I hope everybody can understand it. We will not solve the complicated systems of drift diffusion equations. Actually, everything we need to predict the current voltage characteristic of a field effect transistor is Ohm's law, the proportionality between current and electric field. We will ignore diffusion for a while because it's not much important in the on state. And there is a relation between carrier density in a field effect transistor and gate voltage. So how roughly the field effect transistor works? I will sketch again its schematic. Let us consider n-doped contacts and the induced n-channel within the p-doped substrate. Here we have the contact of source, here we have the contact of drain. There is an insulator layer and there is a metal gate G with the gate voltage Vg greater than 0. The source is typically denoted as grounded one, and typically you apply voltages to the drain. Here we consider the case of positive drain voltages. How it actually operates, how can we explain on the formula the transistor action? The transistor action is based on changing the carrier density in the local Ohm's law. And this carrier density is a function of gate voltage. Why it is a function of gate voltage? Because the gate can attract extra carrier density. By applying positive gate voltage, you increase carrier density here. And the proportionality coefficient in Ohm's law, the proportionality between current and field, becomes depending on the gate voltage. Mathematically, this is described by a very simple relation. To find the carrier density in the channel, you can consider your field effect transistor in each part as a local capacitor. So let's consider the part of a field effect transistor which is located in the vicinity of point with coordinate x. Then you can write down that the voltage drop between gate and channel, let's denote the channel potential by phi, this voltage drop would be proportional to the charge on the plates of the capacitor. We can write that the capacitance multiplied by the voltage drop is nothing but the accumulated charge. There are some subtleties in this equation. The first subtlety is that the capacitance and charge are computed per unit area of the transistor. So why per unit area? Because the real transistors are three-dimensional. Their gate, source, and so on are continued in the perpendicular direction, which we denote as y direction. And there is also z-axis, which is normal to the gate. So this capacitance is per unit area of the gate electrode, per this unit area. And of course the charge is per unit area. The dimensionality of this charge is coulomb per meter squared. The dimension of this capacitance is farads per meter squared. And the capacitance per unit area, which is dielectric constant background vacuum permittivity divided by distance between metal and insulator. This capacitance per unit area should be multiplied by potential difference and gives us the charge density. So how can we derive current voltage characteristic from here? We can express the current density and introduce it, or we can express the charge density and introduce it into the expression for the current. We get something really interesting. The current density is capacitance per unit area, let me denote it as C divided by A, multiplied by gate voltage minus local voltage in the channel, and multiplied by mobility and multiplied by electric field. Could you tell me how can we exploit this equation to find real current voltage characteristics? Because the real problem is to find current if you know the drain voltage and gate voltage. But here you have too many unknowns. Of course, you see Vg here, but drain voltage doesn't appear in this equation. Instead, you have some strange local potential phi, which can depend on observation point x, and electric field can also depend on observation point x. Can we rewrite it in any useful form? Do you have any ideas? Please, anything.
Maybe write the continuity equation and the Laplace equation.
So you think we should take some extra equations like continuity and Laplace equation, yes?
Mm-hmm.
Well, this is a good idea, but what we have on the bottom is the approximate solution of the Laplace equation. What is Laplace equation? It is something that relates potential to the charge density. Of course, it is Laplacian phi equals minus 4 pi rho, but if you consider this as a capacitor, you can write immediately an approximate solution to this equation, which is the voltage drop equals charge density. So the Laplace equation is already here. The continuity equation is more interesting because it tells us that J as a function of coordinate should be a constant, strictly a constant if you have a DC current. How can we use it? Now let us turn it into something useful.
Maybe you can calculate it on the drain where you know phi as a V drain.
Yes, it's a good idea. It is almost what we need. So you would like to apply this equation exactly at the points where you know the potentials. Of course, it should be supplemented by the boundary conditions. Here it equals 0 at the drain, and here it equals Vd. So you can try to apply it successively at 2 points, on the left and on the right. But what should we do with the electric field, which is unknown? Okay, So you have almost obtained a correct answer. Можно сфокусироваться еще побольше, чтобы вот этих вот кусков не было видно, потому что сейчас формулы будут важнее. Да. Okay, we would like to eliminate the electric field via its definition. Electric field is nothing but minus derivative of electric potential with respect to the coordinate. How can we rewrite this equation? Current multiplied by differential of coordinate equals capacitance per unit area multiplied by mobility multiplied by local voltage drop or local voltage and multiplied by differential of voltage. And this equation can be integrated from the beginning of the channel till the end of the channel. The coordinate changes from 0 to channel length, while the potential is changing from 0 till the drain voltage. And this is a simple integration procedure. There is constant and linear function on the right hand side. So after the integration you get that J equals capacitance per unit area divided by channel length multiplied by mobility and multiplied by a simple quadratic function VGVD minus VD squared divided by 2. So your idea to use the boundary conditions was fully correct, and we indeed used them upon integration, and your idea to use continuity equation was fully correct because the current was independent on the coordinate, and this enabled us to make simple integration. Actually, the coordinate independent current can be factored out from the integration sign. This is the final current voltage characteristic that we would like to know. It captures several important features of the conductivity in the field effect device. Please ask any questions about these equations, otherwise they will be erased and we will pass to the plots. Could you speak louder? If no questions, we will pass to the next slide. How it looks like and why it is physical and why it is good. The current voltage characteristics first grows with application of the drain voltage and then goes down. Then it reaches the saturation point, and then, according to the predictions of our theory, it should go down. This go down is not physical. Actually, our theory works well till the maximum point. Then it becomes non-applicable. We will understand soon why is it so. But till the saturation point, it works well. The other thing that the theory predicts well is that when you apply larger gate voltage, you get larger current in the channel, larger gate voltage, and smaller resistivity. The slope of current versus drain voltage becomes higher when you apply higher gate voltage. And this is one of the good predictions. What the theory predicts also is initially your current voltage characteristic is linear, but then it deviates from the linearity to the downward side. So when you apply more and more drain voltage, your transistor becomes harder to conduct. And finally here, however drain voltage you apply, you won't get higher current. Actually, this can be explained, and the explanation involves the very familiar capacity arguments. According to the capacitor approximation, at each point of your channel, the local density of conducting charges is proportional to the local potential. So let us consider the situation where you have large drain voltage plus VD and positive gate voltage plus VG. Why we would like to explain why the current voltage characteristic goes down and finally reaches the saturation. Let us try to see how many electrons are there in the beginning of the channel. In the beginning of the channel, the local potential is approximately 0. So the number of electrons here is approximately capacitance per unit area multiplied by gate voltage and divided by elementary charge. The number of electrons is relatively high here. When we would like to see the number of electrons in the right section of a field effect device, it will be given by a different expression. The potential here is roughly equal to the potential of the drain. The potential drop between top and bottom electrons is gate voltage minus drain voltage. So the number of electrons at the drain is definitely smaller than the number of electrons at the source. So the channel is getting depleted when you travel from its left side to its right side. Actually, you can make a plot of this depletion. You can paint the number of electrons versus coordinate, and it is something like that. So the number of electrons per unit coordinate versus coordinate is a decaying function of the coordinate. This effect is called self-gating effect or self-depleting effect. It means that the potential at the semiconductor itself affects the density in the same semiconductor. This is the reason why the current voltage characteristic of a field effect transistor is deviating from the linear one into the saturating one. Let us see what happens at this point. Let us see what happens at the point where the theory becomes inapplicable. We have derived that the current is a quadratic function of the gate of the drain potential, and we can analytically evaluate the position, the drain voltage at which the characteristic is flattened out. So you just take the derivative of current with respect to Vd, equate it to 0. After simple manipulations, you obtain that Vd equals Vg. The saturation point is where the drain voltage is approximately equal to the gate voltage. But there are bad things happening at this point, because if Vg equals to Vd, then the number of electrons at the drain should turn to 0. It means that the drain side of the transistor becomes very, very poorly conducting. Afterwards, when you apply larger voltage, according to our theory, the number of electrons should become negative. Of course, it cannot be. Of course, it cannot be because just by definition, the number of electrons is a positive quantity. Can you make any suggestions how can we fix the theory? What works poorly? Why it predicts negative electron densities? So what is so wrong in our equations that the theory predicts negative electron densities and degrading currents with application of voltage? What are our errors and assumptions? Come on, there are a lot of assumptions, at least when we wrote the basic equations. What we did when we wrote the basic equations, we used some simple Ohm's law and very simple relation between voltage drop and carrier density. Why is it wrong? Okay, there are several things that are going wrong in this derivation. The charge density that appears on the right-hand side of the capacitor relations is contributed both by electrons, charged donors, and probably holes. And the signs with which they appear in these equations are positive sign for M and negative sign for P. When we consider the Ohm's law, there are separate currents for electrons and holes, and these currents are additive. So currents carried by electrons and holes should be summed up. So you see that when you approach the point where the density of electrons is low, then it should become comparable to the donor density or to the hole density. So when your electron density approaches zero, then you need to recall immediately that you have always some number of holes in semiconductor. It looks that these equations are not solvable together, but they indeed are, because when you introduce holes, there are two unknowns here, N and P. Here are also N and P. You have too many unknowns, but in reality the situation is simpler. Both electron density and hole density can be expressed as a function of Fermi level, and the Fermi level is the same for electrons and holes if they are strongly interacting, if they are strongly recombining. And actually there is only one unknown, which is the quasi-Fermi level, and the equations can be resolved with respect to it. There is also a more consecutive, the more strict theory for this relation between carrier density and the potential drop. I am actually surprised no one asked about the dimensionality of the quantities that we are working with. In this relation, the charge carrier density should be measured in units per area. So this is the areal carrier density, number of carriers per meter squared. So if we introduce the areal density of electrons per capacitor plate, then we get the current in amperes per unit width, current per unit width. We didn't get used to this kind of expressions because in local Ohm's law, in real Ohm's law, J equals sigma E, the current was per unit area, and the conductivity was the bulk conductivity. Typically we got used to the bulk laws, and our semiconductor in a field effect transistor is bulk. But strangely, we use the two-dimensional quantities like the number of charge carriers per unit square and the current per unit width. This can be explained. This is not so bad because Actually, when we work with the current voltage characteristic, we can write it locally like three-dimensional current equal the three-dimensional density multiplied by charge and multiplied by electric field for each point in the channel, which is characterized by coordinate x and z. But when we want to calculate the full current in the device, which is carried here, here, and here, we will need to integrate the three-dimensional currents with respect to the vertical coordinate. So we can expect the current to be large here, smaller here, and smaller here, and so on. So to get the full current, let's denote it as J2D, we need to integrate the current at each z point with respect to that coordinate, for example, from 0 to minus infinity. Three-dimensional density, depending on that, multiplied by mobility, multiplied by electric field. We can assume that everything except for the carrier density doesn't depend on the vertical coordinate and take it out. What we get finally is mobility multiplied by electric field, multiplied by elementary charge, multiplied by the integrated three-dimensional density over the vertical coordinate. But the integrated three-dimensional density is nothing but the density per unit area N2D. So this is the microscopic justification to use the relation between current per unit area and carrier density per unit area. Namely, these quantities appear in the capacitor relations. Now it would be tempting to formulate a more rigorous theory for calculation of charge densities and for the calculation of current voltage characteristics, because we saw a simple approach. The simple approach works fine, but it doesn't predict that the transistor saturates to finite current, and actually doesn't predict the presence of the off state, because what we got that current is capacitance per unit area per unit channel length multiplied by gate voltage drain voltage minus Vd squared divided by 2. We expected initially that when the gate voltage is 0 or small, the conductivity should be exponentially little, and we don't see it here. Whichever gate voltage we get finite conductivity. We don't get exponentially small conductivity. But to get with exponentially small conductivities, we need to accurately calculate the charge carrier density. This is doable, and you can do it by solving the Poisson's equation for our field effect device structure in the vertical direction. So there are some explaining band diagrams. What I try to explain here, what I plot here, is the cuts of the potential energy profiles in a field effect transistor in the vertical direction. Here is the insulating layer, here is the gate layer, here is the p-doped substrate, and here are the contacts. The contacts are not very interesting here. On these graphs you see the dependencies of electron potential energy on the vertical coordinate z, which is directed from metal toward insulator and toward p-doped semiconductor. When we have no voltage. When we have equilibrium, this is almost the Schottky junction. But the Schottky junction that we have previously considered is the Schottky junction of metal and p-doped semiconductor. So it had an upward bending of the potential profile at equilibrium. What we have here is the Schottky junction between metal and p-type semiconductor, so it has an inverted band bending. And the energy barrier is for holes. When we apply positive voltage to the metal, then the potential energy at the metal side for an electron gets lower. And this potential is pulling all the potential band profile to the downward direction. And when gate voltage is positive, there is a potential well for electrons formed in the vicinity of the insulating layer. And well, finally, at very large gate voltages, you can even get a situation that your potential profile would cross the Fermi level for electrons. Why this situation is called inversion? This is because the type of conductivity is P in the bulk, but it is N at the surface. According with our simple arguments that the application of positive gate voltage results in the formation of negative charges in the vicinity of the surface. You can also consider some other signs of gate voltage. For moderately negative gate voltage, you can flatten this Venn diagram out, so there is no energy barrier, and you can also make an accumulation regime where you make large negative gate voltage and you attract many holes in the channel. But for N-type contacts, only this regime is good conducting and all other regimes are poorly conducting. To make a good theory for the conductivity and charge density, you will need to write and solve the Poisson's equation for this structure in detail, without the plate capacitor approximation, just by solving the Poisson equation with respect to the full distribution of electric potential as a function of Z. This is indeed doable. I will show you one important trick how we can solve it. It is applicable to many kinds of differential equations of the Poisson type that you are facing when work with the semiconductor theory. So what we need to find? We need to find the distribution of electric potential and associated electron density throughout the field effect transistor structure as a function of Z coordinate. The Poisson's equation looks like very simple. Second derivative of potential equals 4 pi E multiplied by the carrier density. The carrier density is contributed by electrons, holes, and acceptors. Acceptors appear because initially the semiconductor was p-doped. The statistics, we assume that the semiconductor is in non-degenerate regime, so the statistic is Boltzmannian. It is not a Fermi statistic, it is degenerate into Boltzmann one. And then if we assume the potential to be 0 at the infinity, then the number of electrons at finite coordinate Z is the number of electrons at infinity multiplied by Boltzmann exponent, and the same for holes which have negative Boltzmann exponent. The boundary conditions are the potential at 0 Z coordinate is equal to the gate voltage and the potential at infinite coordinate is equal to 0. How we can simplify it? By rewriting it in dimensionless form. Let us introduce a new variable phi large, which is electric potential multiplied by unit charge divided by kT. If you rewrite this equation in terms of phi large, you will get something like that. Second derivative of dimensionless potential equals something with dimension of inverse length squared. This something will be explained. Well, this is just scaling procedure. Then you have exponent of phi large minus density of holes divided by density of electrons multiplied by exponent of minus phi large and plus acceptor density in terms of electron density at infinity without any factor. After the scaling procedure, you get the inverse length Ls squared equals nothing but 4 pi p squared divided by kT and multiplied by electron density at infinity. This is nothing but inverse screening length. But what is really complicated in this case that the formation of inversion layer is a highly nonlinear process. So you cannot linearize this equation assuming the potential to be small. You should take these all these exponentials exactly, and you should handle them exactly to describe the formation of inversion layer. But it is still doable. To do this, you can multiply both parts of equations by phi prime and recast it as full differentials. After that, you get differential with respect to z of the quantity phi prime squared divided by 2 equals 1 divided by screening length squared, differential with respect to z of exponent of phi plus p infinity n infinity exponent of minus phi plus na divided by n infinity phi itself. And now, using the boundary conditions, this equation can be integrated once more. It can be integrated from some point with coordinate z till infinity. So you integrate it from z to plus infinity. What you get as a result? You get and phi prime is nothing but electric field. Phi prime squared at infinity minus phi prime squared at some point z divided by 2 equals 1 divided by screening length squared. What we have at infinity the potential equals to 0. Then we have 1 plus p infinity divided by n infinity minus exponent of phi minus exponent of minus phi minus na to n infinity phi. We can further simplify this equation because phi prime is nothing but electric field deep in the semiconductor bulk, and it equals to 0 because the state is, well, established. The state is equilibrium. We managed to reduce the order of differential equation from the second one to the first order one. Actually, we could integrate it once more with respect to dz and get the full distribution of electric field and electric potential throughout this structure. This is a good home task to do it, but to get the density of electrons at the surface and to get the full electron density, this is not important, because we can apply this equation to one certain point. Let us apply it to the point where Z equals to the thickness of the semiconductor. Then at the right side you will get nothing but the potential at the semiconductor surface, and on the left side you will have the electric field at the semiconductor surface. This electric field is simply related to the gate voltage. The electric field at the semiconductor surface is, well, coming back to dimensional units, it is E divided by KT multiplied by electric potential differentiated at Z equals to D. We can simplify using the continuity equation for the D vector. We know that D vector is continuous at the surface. Then dielectric constant of the semiconductor multiplied by derivative of electric potential at the semiconductor surface should be equal to dielectric constant of the insulator multiplied by electric field at the in the insulator. But the electric field in the insulator is nothing but gate voltage minus surface potential divided by thickness of the insulator. So we can express the derivative of phi at the surface of the semiconductor via the gate voltage itself, E divided by KT multiplied by epsilon insulator divided by epsilon of semiconductor multiplied by gate voltage minus surface potential divided by thickness of the insulator. So what we got by applying this equation at the point D, we immediately get the potential at the surface of the semiconductor, and we at the same time get the number of electrons at the surface, and we can calculate it everywhere in the structure. So frankly speaking, this equation is complicated. It is a transcendental equation. It is not as simple as we wrote before, like CVG minus V phi equals En. It is a tougher equation, but still it predicts the densities of electron and holes more accurately than the previous equation did. I think this is quite enough for today. On the next lecture, we will continue with numerical solution of this screening problem. We will see how the transistor indeed operates in the off state, and we will also get back to our initial problem, why short devices mean fast devices, and why scaling means higher operational frequencies.